So this is going to be the last video of chapter 10. And what we're going to finish up with is we've been focusing on the ideal gas law. So how does this actually behave in a real world situation? Okay, so what we have is a discussion of ideal versus real gases. And this is in the last section of chapter 10. So if we take PV equals nRT, okay, if I were to take pressure and volume and put it over R and T, I get a numerical value of 1 because we're saying this is equal to this. So what I'm going to show you is this graph, and this graph is in your book, but it's also in your notes. But I'm going to go to the one that's in the book because I'm going to like it for a couple different reasons. So first off, I have pressure and atmospheres versus these 4 different gases, okay? And what it's trying to show is, depending upon what the pressure is, it's going to veer off what we call the ideal gas law, okay? So pause here for a second. So this is the picture that you see in the book, nice and colorful and everything else. So what you want to see is once you get to higher and higher pressures, these gases start to veer away from the ideal gas law, so they don't behave ideally. But what I want you to copy into your notes, and this is why I brought up this picture, is once I get close to atmospheric pressure, which is 1 atm, everything starts to behave like an ideal gas law. So that's what these lines are kind of converging, and then they kind of end up being exactly like the ideal gas law. So please draw a little box next to your graph to kind of show this. So here I drew my box over here. It's not as colorful as the one in the book, but it's trying to show you again, high pressure situations, they veer off, but when we're at normal pressures, they behave like the ideal gas law. Now the second graph that I have in your notes is this one, okay? So this one is trying to show a particular gas. So let's say it is nitrogen gas. Let's say that this is nitrogen gas at 3 different temperatures. So this is 200 Kelvin, this is 500 Kelvin, this is 1000 Kelvin. And we have our line here, and we have different pressures in atmospheres. So what this is trying to show you at 200 Kelvin versus 500 versus 1000 Kelvin, the higher the temperature, the closer I'm getting to that one. So if I were to draw a line in here at a much higher temperature, say 1500 Kelvin, you would see that the line would get closer and closer to the optimal one for the ideal gas law, because temperature is going to be proportional to the speed of the particle. So the faster the speed, we're going to have that. So what you can put in your notes is real gases behave only like the ideal if you're at low pressure, so you could say less than 1 atmosphere, and at high temperature. So again, greater than 1000 Kelvin, if we're using this graph as kind of an example. So that's what these 2 graphs are trying to show you. So at low pressure and high temperature. Reason for that is because particles will be much farther apart. If they're at higher temperature going to mean you have a much higher speed of those particles. So there's going to be less forces that are going to keep them close together. So we have 2 things that we need to account for with real gases, okay? So real gases take up volume, okay? They are matter, so they are going to take up volume. So we need a way to account for that. So we're going to do that with a very simple equation. So volume minus N times B. So B is going to be a constant for each gas, and it's in your book about page 429. And there's a table of constants given for each type of gas, because every gas is going to have a different volume depending upon its size. And N is going to be the number of moles. This is going to be accounting for the gas itself, and this is going to be the container it is in. So again, remember that the ideal gas law, the volume we always use is the container itself. So we can use this equation instead for volume, because we know that gases take up space, okay? We also know real gases have attraction to each other. So we are going to essentially take care of that using N over V. Well, N over V is moles per liter, okay? So that is a unit of concentration we talked about before called molarity, okay? So depending upon how much I have per unit volume, I'm going to have more and more attractive forces, okay? So the higher the concentration. So I can essentially use this equation. So I'm going to rewrite it over here just so we could see it. So it's going to be A is a constant. A is a constant. And again, that's going to be determined by the gas itself. So this is the constant for the gas. And again, that's in a table that we could be looking at. N over V is going to be the concentration, and then it's squared. So why would it have to be squared? Well, that's because you need a pair of particles in order for you to have attraction, okay? In order to have attractive forces, you need at least two particles. That's why you're always going to be squaring the concentration. So this is going to be part of what we call the van der Waals equation, okay? So the van der Waals equation that I've given you, this one, the way it's written, I don't like it as much as I have in this example. So the pressure is going to be affected by the attractive forces, because if you have, so this is the concentration, if you have bigger clumps of gas particles, when they hit each other, you're going to have a stronger force, okay? So the force is going to increase if you have more clumped together or you have a higher concentration. So that is why pressure is going to be essentially affected by concentration. And then this is your volume, and this is the gas volume that you're essentially subtracting from the overall volume of the container, is equal to nRT. So the pressure is affected by concentration, so that's the attractive forces. The volume is affected by the gas volume, subtracting that out, okay? So this is called the van der Waals equation. So I will give you A and B and all of that stuff. I'm not gonna have you do the math. We're gonna do the math just to kind of have a conversation, okay? So calculate the pressure exerted by 0.5 moles of nitrogen on 1 liter container at 25 degrees Celsius. And I will be specific as to when you have to use the van der Waals equation. So I'm going to pause the. So if I use the van der Waals equation, and I will be specific, but I'm not going to have you really do the math with this. So I have an A and a B given here, so I could find the concentration of 0.5 in 1 liter. I'm going to square that and multiply that by A. And then my volume is 1 liter. I'm going to subtract the 0.5 moles of that gas times its constant. Again, the constants are going to be related to the particular gas. Is equal to the moles, 0.5 times R times T, the 298 Kelvin. So when you plug that all in, you get a pressure of about 12.1 atmospheres according to the van der Waals equation, okay, accounting for the fact that it's a real gas. Well, what if you were trying to solve the pressure using PV equals nRT? Okay, what if you did that? Well, if you use the ideal gas law, PV equals nRT, nRT over V, it would be 0.5, 0.0821 times 298 divided by the 1 liter. So you get about 12.2 atmospheres, okay? So as you could see, there is not much difference between these two values, okay? So, and that is because under normal pressure conditions, pretty much everything is going to much follow the ideal gas law. So the reason I have you do the math here is just to prove to you that yes, real gases are really what we're dealing with here, but the ideal gas law is going to work unless I have really high pressures or really low temperatures. Then I really don't have ideal gas law being followed. So again, you're not really going to have to use the van der Waals equation. I will give you this equation. Instead, I'm going to have you explain it or explain what it's fixing with the ideal gas law.